Hi guys, and welcome to this tutorial video, the tutorial video on generalized linear models. Linear models are more common models that are used in econometrics. So in some situation, you can notice that linear regression is not appropriate in a situation such as actuarial modeling. In some situation, variable tend to not be significant in when we estimate dependent variable with linear regression model, and sometimes when you apply, for example, the logarithm in a dependent variable model begin to be a linear regression seem to be very appropriate due to the increase of R square, for example, or any significance parameter of the model. So in some situation, we need to apply some transformation in the mean of our dependent variable in order to make a model linear. That in this which situation we talk about generalized linear model. So first of all, we need to know that generalized linear model have so it's a class of a linear model that are made up of three main components. So we have random component, we have a systematic component, and we have a link function. That are the three main components of generalized linear models. So in random component, we just identify dependent variable y and its probability distribution. We identify a main component of our variable. Maybe we just want to express the GDP in function of capital and number of hour of works. So maybe expressing a GDP in function in linear manner in function of capital and number of hour of works look to be not very interesting in a way that you can find out some linear hypotheses such as error term normality cannot be verified, or other hypotheses that are hidden behind a linear model. So you have, for example, Cox-Douglas transformation that can lead you to the log linearization of our equation in order to obtain a linear equation between the logarithm of production and function of capital and number of hour of works. So we have also a systematic component. The systematic component just identify the set of explanatory variables that are the variables that are in empirical and in the literature are the variables that can be explanatory, can explain the variation, the fluctuation of a random component y. So after setting the different factor that can influence the fluctuation of our random component, which are explanatory variables, we need to search for link function. In the case of Cox-Douglas function, for example, as I told you very earlier in this tutorial, you can just apply the logarithm in our function in order to make a relationship linear between the dependent variable, in which case we took the example of the production, between production, in fact, and dependent variable that are capital and so on. So you need to identify a link function G so that J apply to the mean of random component set a linear relationship between our different the mean of our dependent variable and the dependent variable. So we have so many examples of random component. So we have a conditionally normally distributed response with constant standard deviation. We have a regression model that fit so far. The regression model in this situation, we have identity function as link function. So we also have binary outcomes. We have success and failure. So random component, it has binary distribution, and model is called the logistic regression. In logistic regression, we need to model the probability of success or a failure of our events, of our phenomenon. So linear modeling of probability is not very interesting, because the probability is just a variable, a quantity that is between 0 and 1, and model it with linear representation is not it's not very good. So we can use, for example, what we call the logistic function. Logistic function is the expression of our variable in function of some expression depending on exponential of the linear combination of our variable, and we'll come back on it a little bit further in this tutorial. So in this situation, by applying the logistic link function, we obtain a linear representation of the mean of our dependent variable. So we also have a model that counts data, that model that count number of events in fixed area and length of time. So we have random component which have a Poisson distribution, and model is called Poisson Regression. So when count data have a variance which is higher than the mean of the variable, the model cannot be fit with negative binomial regression, because in the case of Poisson regression, one of the main hypotheses hiding behind Poisson regression is that the variance is equal to the mean of the random component of our variable. So, which while this hypothesis is not verified, we need to look, for example, at negative binomial regression. We also have continuous data with skewed distribution, and variation that increase with the mean can be modeled with gamma distribution. So we have some common link function. We have identity link, which is used in normal and gamma regression model. So we don't need to transform really component our target in order to have linear estimation. So we also have link function, that logarithm that I also explained to you about very earlier in this tutorial about, for example, coupled class modeling, or in actual situation, log link is most used in actually in the modeling of probability, in the modeling of claim of claim. So claims amount by the person in charge of in the insurance company. So we have also logistic link in the case of logistic regression. So we have a probability that can be expressed in function of exponential. So we can apply the probability can be expressed in function of some exponential function of the linear combination of explanatory variables, so that in applying logistic link we have a linear representation of our probabilities. So in case of logistic regression, we have a dichotomous response variable and numeric or categorical explanatory variable. So the goal in the logistic regression is to model the probability of a particular outcome as a function of predictor variable. So you can see that logistic regression is one of generalized linear regression model. But the problem here is that the probability are bound between 0 and 1, so that we cannot just express the probability in linear manner between function of explanatory variable, that some of them can be even categorical, not only linear. So if we just express the linear relationship, we can found of negative or more than one probabilities. So it's not good according to the probability theory. So the distribution of response is binomial. So the link function is given by on your screen, the link function of logistic regression. So we will explain to you in a minute. So when we look at probability, so the probability expressed in this manner. So we take a case of only one explanatory variable, and in this case we took a case of numeric variable. So if we express the probability as the relationship P of X suggests, so we can see that in the two eventuality of which are presence and absence of a characteristic, we can see that in this situation the probability of the presence is 1 minus the probability of absence using this relationship. So this is the probability of presence of the characteristic that is expressed in function of exponential of the linear combination of explanatory variable, in which case we have only one explanatory. So when we apply this link function to our probability, we found that the transformation of the probability which link function that is here lead to the linear representation of our probabilities of when we make a transformation. So beta 1 is a coefficient which is called which can have many values. When beta 1 is equal to 0, it means that the probability of present is the same at each level of the variable x. When beta 1 is positive, it means that the probability of present increase as x increase. So in the case in which beta 1 is negative, it means that the probability of present decrease as x increase. So that's the logistic regression, and in logistic regression we can just estimate our parameter beta 0 and beta 1 using some statistical software such as SAS, R, Stata, SPSS, and so on, using the maximum likelihood method. So the primary interest is estimating the and testing hypotheses regarding beta 1. Large sample tests. We use word test in large sample when we have large sample. So the test statistic is given by the square root, the square of the ratio beta 1 over the variance of beta 1. So we can note that when this statistic follow a chi-square at 1 degree of liberty. So when observed statistic test is superior to critical value of chi-square of 1 degree of liberty with threshold alpha, we can reject the null hypothesis, which is beta 0 equal beta 1 equal to 0. So we also in logistic regression we have odds ratio. So the odds ratio is indicator that is used to interpret a regression coefficient. So in linear regression, the slope coefficient, for example, is the change in the mean response as x increased by 1 unit. But in logistic regression, we can show that the odds ratio, the odds of the probability of events divided by the odds of the probability of so the order of the probability of the presence of effect and the probability order divided by the order of the probability of absence is the odds ratio, and we can demonstrate that this odds ratio is equal to the exponential of coefficient beta 1. So exponential of beta represents the change in the odds of the outcome by increasing x by 1 unit. So if beta 1 equals 0, we can say that odds ratio and probability are the same at the x level, So when beta 1 is positive, which means that exponential of beta is superior to 1, it means that the odds ratio and probability increase as x increase. In the case in which beta 0 is negative, which means that exponential is inferior to 1, the odds ratio and the probability decrease, in this case as x increase. So we can also compute a 95% confidence interval for all ratio, and that can help us interpret the odd ratio. So if the entire interval is above 1, we can conclude a positive association between our quantitative variable, explanatory variable, and the probability of event. So if the entire interval is below 1, it includes a negative association. And in the case in which the confidence interval contains 1, we cannot conclude there is an association between our factors. So odd ratio is an indicator that can be used to analyze association factor of binary response term. So we can also have a situation of multi-logistic regression. We have an extension to more than one predictor variable, either numeric or dummy variables. So we have K predictors. The model is written as you can see on the screen. Probability is also written as exponential in function of exponential of linear combination of our explanatory variable. So we can compute the adjusted odd ratio of each explanatory, which is the exponential of the corresponding coefficient. So many models have nominal and ordinary predictor and widely made use of dummy variable. So and also test for overall model significativity or coefficient, self-coefficient significativity using some statistic that follow a chi-square law distribution, the chi-square distribution. So another family of multiple linear regression is a Poisson regression. Poisson regression is generally used to model count data. So we have a distribution which is Poisson, and the main hypothesis in Poisson distribution is that the mean of the dependent variable is equal to the variance of the dependent variable. In this situation, the link function can be utilized using the log function, the log link function. The link function is a log function. So I explained to you the case of actual modeling of claim amount in insurance company. So we have the log transformation of, for example, claim amounts that is modeled in linear combination of parameters that can explain the claim amount, which can be the gender, which can be age, which can be in automobile insurance, for example, we can have characteristic of a car. So when we use this link function, it means that the function, the expression of our main variable using the our function link is exponential of the combination of different variables when we come back in our main variable. So tests are conducted in this situation as in logistic regression, and when the mean and variance are not equal, which is called overdispersion, we often replace the Poisson description by the negative binomial regression. So that is essential that I need to tell you about generalized linear model. You can also by your own research right now find many other families of generalized linear model. In our next tutorials, we will show you how to implement generalized linear model mainly in R. So that's it for today. Thanks a lot for listening to all what I